Good morning, YouTube. Needlebender 785 Ohio with another video on the Tsunami Project 4cx5000. And as we're getting closer to that time where we start applying different voltages and testing different parts of the circuit, well, this is one of those times. Just kind of a progress report. The bottom of the deck, I would say, is 98% populated. I got about 3 wires that are left unconnected, and that's because my Amazon delivery guy mixed up the order for my quick disconnects from my meters, so I can't get power to my meters, but I get power to everything else. So the meters are going to be showed in the next video, just because I don't have the connectors. In this vacuum relay that's unconnected, and that's just because I didn't have time. But everything else is connected. I rechecked the input tune and it was totally flat. I mean, the needle did not even move. That's with the tube in and even the bias voltage applied. So let's talk about, this video is going to be mostly how we're going to be powering different circuits, starting of this box, and protections, interlocks that are required for this tube, and different safety circuits that are also incorporated into this design. So let's talk about the basics, basic safety interlocks. So we have this blue MOV, which stands for metal oxide varistor, which is how the voltage is actually fed into the screen supply, which our screen positive is actually the case. Our screen negative is the cathode. And whenever there is no voltage on the screen, there's a 10 ohm resistor that shorts the screen down to the cathode, making a path to ground. Also, should there be any kind of a short, let's say a positive wire, some kind of a positive wire falls and touches the case, well, you have a path to ground through this MOV and a 10 ohm resistor, which are going to be in parallel, and then through this vacuum relay down to ground. Now, whenever certain conditions are met, which we're going to discuss here in a little bit, then and only then you can engage this relay and actually apply screen voltage. Now, the IMAC data sheet talks about a few things that you have to watch for, kind of like not to overdrive the tube, to watch your AB1 versus AB2 operation. But there's one thing that they specifically mentioned several times as the most critical issue for this tube in this configuration. It's not having your plate voltage, i.e. high voltage, on the anode, and having the screen on. That is probably the fastest way to destroy this tube. So there has to be an interlock, and it actually talks about as an interlock to not allow you to turn on your screen until you have high voltage on the plate. So one might think, well, I'm just going to make sure that I have it on before, and some people do that, but here's a really good example that happens to me sometimes on my 3000, and especially when I first built it. You're talking, everything's running good, you're long-winded on the key. Next thing you know, you lost your high voltage supply because, you know, it tripped a little safety switch inside. Anyway, you lost your high voltage for whatever reason. Well, that's not a big deal. High voltage goes, bleeds down, but your screen is still on. You're not fast enough to hit the switch, and you cause damage to your tube. So we have a solution for that. So we have a voltage sensing circuit on the high voltage side that sends a voltage signal from 0 to 10 volts. 0 to 10 volts. And one of the first stops it makes is this little circuit. Now, this is a LM393, which is a comparator. It takes a voltage and compares it to the preset value. If it's below preset value, the little relay is not engaged. Very simple circuit. If it exceeds the little value, which I have mine set to 5 volts, which is equivalent to 5 kV on the plate, we basically don't want to have anything going on the screen until the plate is at 5 kV. And we have this little interlock. So for some reason, and the voltage is not even fully down, it goes down to 4 kV, this trips and it closes this, it opens it opens this vacuum relay, and you instantly don't have your screen voltage and the tube is protected. It also will not let you turn on your screen until you have proper high voltage, and we're going to go through the demonstration here a little bit as we have this high pot tester going on. Just for the demonstration purposes, we're not going to be actually applying any screen or grid voltage. The box is actually fully depowered. The only thing is going to be that's going to be powered up. So it's powered by 12 volts, so we can operate all the relay circuitry and kind of do a demonstration. So you come up to this box and it's totally cold, it's not running. Obviously you would have to turn on, my power supply is separate, so you have to engage your power supply, but the power supply is actually not turned on, it's turned on remotely, which is one of these relays will remotely turn on the power supply. You put your power supply in standby, it's running, the fans are running in the power supply, but the power supply does not actually provide any high voltage until you ask for it. So my logic in these switches can do a couple of things. So they have a switch and they have an indicator. So I didn't just wire the indicator directly with the switch. In some instances it's exactly what it is, but when you push the button, you're asking the box to do something, and when that condition is met, that's when the indicator turns on. All of these switches actually operate relays, so there is no 110 volts. This is all controlled by 12 volts here. And all these 12 volt relays are controlled by these switches. But not all the indicators are just powered by the switch. Well, this first one just happens to be you're applying 12 volt power and turning on your blower. So obviously the blower is disabled at the moment. There's no reason to have all this wind, and the box is unplugged. And so as you can see, the condition is met, and the box is actually the fan will be turned on. When you turn on the fan, next thing you want to turn on is your filament, and this just turns on your filament. So you can see that there's nothing happening because we have a step start circuit, and only when the step start is complete does this illuminate. Let's try that again. You push, you ask the filament to be turned on. However, the actual indicator is not turned on until the filament is fully on. So that's a little logic I put together. Next is the high voltage switch, which asks the power supply to provide high voltage. So again, you're asking for the high voltage, but right now there's no high voltage, so it's never going to turn on, and it's never going to let you turn the standby operate switch, which would actually engage the screen. So you can't engage the screen since there's no high voltage. So you're asking for it, and there isn't any. But let's go one step further. Let's ask for high voltage, and we're going to simulate here. We're going to turn on this supply. We're at 3.5 kV at the moment, and we can see that there's no this is a variable current, variable voltage power supply. So we're going up in power, and we're going up in voltage, and we hit 5 kV. There we go. 5 kV, we have high voltage. And this little indicator says that we have proper high voltage. Only then we can turn on our screen, which is part of the standby operate. This is your standby operate circuit, which actually engages the screen. But also, let's say it's kind of kind of a corny secondary, maybe even a third safety design, but let's say you wanted to shut off the high voltage and it didn't do that, and it didn't do that, and it didn't do that, and so the indicator would still stay on, and because you still have high voltage present. So it's actually, the indicator is predicated on having a presence of high voltage on the plate. So you're asking for the relay to close, you're commanding the power supply to bring up your high voltage circuit. As it's bringing up, the indicator turns on, allowing you to do this, which is your standby operate switch. Alright, so kind of didn't mention this earlier, but the filament has a resistive circuit, timer circuit, allows the filament to warm up before it is fully switched on. Just a little step start circuit allows the filament to kind of come up to temperature. So a couple of things I got to do is I got to don't need our high voltage supply anymore. Got to wire up this. Got to wire up this vacuum relay, which is going to actually provide power to the screen. Wire up these meters. In the next video, we're going to be doing a tube burn-in with this thing hooked up, making sure we don't have anything crazy going on with the actual tube. We're going to be simulating very low current application, probably like less than 5 milliamps, just to make sure the tube is stable. And I love this thing. This thing is great. You can literally see if there's no sparks. This thing doesn't make sparks. If you have, if you're drawing current, if you can set your current limit. If you're drawing over that kind of current, voltage will go down to 0. So and this is a positive / negative, 0 to 20 kV, 0 to 30 milliamps. Right now I have it set to 5. So it will not produce more than 5 milliamps of current in this configuration. That's what we want. When we put the tube in and actually apply this voltage, we don't want to see any kind of current draw, so that's what we're testing. And it's always nice to test all this stuff with actual high voltage, but without having a whole bunch of current from your real actual operational power supply. Just even if you did have some kind of short circuit, it would just immediately show it to you here, and it would not hurt anything, which is what we're looking to do. Anyway, stay tuned for the next video. But we're getting close to having this thing power up and at least do the burn the tube in for 24 hours. And I got the tank circuit built. I got most of the stuff done. But anyway, we'll see you in the next one. Needle Bender 785 Ohio, back on the side.